astronomers meeting. And I swore, didn't we have the last one just like last week? So they just go faster and faster and put time to spare. Anyway, I am Charlie Nielsen, president of the club. We have a few other officers in the room, and I'd have to check maybe some on Zoom, and we might get some reports on that later. But as tradition would have it, we always have our guest speaker first. In the event that somebody just wanted to have that part and didn't want to stick around for a highly entertaining business meeting afterwards, we probably would let you escape, so, and not take it personal. So our speaker tonight is Dr. Fan Zhao, who is currently a postdoctoral research fellow in the Department of Astronomy right here at the U of M, the national champs, by the way.
Yes.
Prior to that, he earned his PhD at the Pennsylvania State University in 2024 and his Bachelor of Science at the University of Science and Technology of China, and that was in 2019. Broadly speaking, Fan is interested in massive black holes and galaxies. His research strongly focuses on multi-wavelength data covering from X-ray to radio. Fan works in multi-wavelength observational astronomy with research focusing on massive black holes and galaxy centers, including their physics, coevolution, and demography. His work utilizes observations from many facilities at the forefront of astronomical discovery, such as Chandra, XMM Newton, and in the near future, the Rubin Observatory's legacy survey of space and time. Dr. Zhao has come to us tonight to talk about his black hole research. The title of his presentation is The Cosmic Growth of Massive Black Holes, Insights from Deep Cosmic Survey. So let's give him a warm welcome. Before I get started, I want to do a shout out for Don Foley for getting our speaker tonight. And I believe he also got us our February speaker too. So thank you, Don. You're on.
Okay. Yeah. Thank you for the very good introduction. For inviting me to be here, and thank you everyone for being here for the talk. So I'm basically going to talk about black holes and specifically the black hole evolution across cosmic time. And I will talk about this topic mainly from observational perspective. And at the top, I highlight several important facilities that I've been using, including the Rubin Observatory, the Chandra X-ray Observatory, and the XMM Newton. And I will talk about them later. But first, black holes, I assume that some of you may have heard the term black hole. So it's a very exotic type of object in the universe. And I think it's worth spending some time giving a very brief introduction of what they are and why we care about them. So, black holes are basically a huge concentration of matter packed into a very, very tiny space. Okay, just let's say if we want to make the Earth to be a black hole, then we need to compress its radius to be smaller than a quarter coin. So it's very, very compact. That means the density is so high and the gravity is so high that even light cannot escape from a black hole. So this is why they get the name black hole. And these are very extraordinary objects, but actually they are quite simple physically. They are unlike our ordinary objects like the computer desk unit to describe what they are made of, what their shape, etc. But for black holes, we only need three parameters to describe them. It's called the so-called no-health theorem. We only need three parameters. That's the mass of the black hole, the spin of the black hole, and the electric charges. And for astrophysical black holes, usually the electric charges can be neglected because it's neutral, it's electric neutral. So we don't need electric charges. And for if we are sufficiently far away from a black hole, its spin also does not matter at all. It can only what really matters is its mass in most cases. So actually for astronomers, the most important one here is just the mass of the black hole. That's sufficient in most cases. So because of this, people have divided black holes based on their masses into some categories. Here I'm showing the mass spectrum of compact objects, and the unit here is the solar mass. Okay. So at the solar mass, the mass of the sun, we have compact objects like white dwarfs and neutron stars, etc. And if we go a little higher, then we have stellar mass black holes. These stellar mass black holes can go up to like 100 solar mass. Then that's the kind of the limit. In this talk, I'm going to mainly focus on the so-called massive black holes. And the definition is that they are more massive than stellar mass black holes. In other words, their black hole masses are about like 100 solar masses. And people actually have so the reason for dividing that is because massive black holes and the stellar mass black holes have very different physical origins. The stellar mass black holes, they're kind of produced by dead stars. When massive star die, it will explode and leave a remnant of a black hole. So that's the stellar theory. But to produce massive black holes, we need other ways of doing that. People have further divided the massive black hole into two subcategories. One is in the rightmost direction. That's the supermassive black hole. They have black hole masses about like 1 million solar masses. They can reach far more than like 1 billion solar masses or beyond. So they are very, very massive. And in between, we have the so-called intermediate mass black hole. That's basically mean that they have masses between the stellar mass black hole and the supermassive black hole. The intermediate mass black hole have masses like between like 100 1 million solar masses. And you can see that there is a question mark here for intermediate mass black hole because currently we have very, very poor understanding of this intermediate mass black hole population. And this is a very hot topic right now. I think it's people begin like work on intermediate mass black hole for only about like 10 years or so. But for supermassive black holes, people have been studying that for several decades already. But how do we actually detect massive black holes? We can just go to the definition. So they have lots of masses within a small region. So we can try to detect the gravity. And that's the so-called dynamical measurements. We want to detect the dynamical influence of its huge mass. And a very well-known example is the center of our own Milky Way. We have a supermassive black hole in our own Milky Way. The mass is about like 40 million solar masses. Maybe 4 million. I don't quite remember that, but it's a supermassive black hole. It's called Sagittarius A star in our center of the Milky Way. And people have been monitoring that for many years. It's already 3 decades. And this plot here basically shows the trajectory of individual stars in the very center of our galaxy. And it's 30 years trajectory. And you can see that these stars orbit around some common center. Like here, if we look closer, that's here. And based on this, we can measure the mass of the central supermassive black hole. It's just like the sun, the Earth orbits around the sun. We have stars orbit around the black hole. And that's a very convincing evidence showing that there is something there. And also we can measure the size of that. The size cannot exceed the closest point of the trajectory. So just based on some calculation, we know that normal matters can explain the huge mass, so it must be a supermassive black hole. And actually, this is independently confirmed. I think this figure is very famous. It's a direct imaging of the black hole in our own Milky Way. So we indeed see that there is a black hole. there is really a hole there. So that's a very extraordinary discovery. But I have to say that it's very expensive to constrain the existence of black holes with dynamic measurements. We need very long exposures, and also in this time we need a long timeline, like 30 years to track the trajectory. And also we need very high angular resolution. So if we go a little bit far away, it is very difficult to do such type of measurements. So people have actually using the other way to find massive black hole. Then that's actually the main way of finding massive black hole. That is their photons. So black holes are dark, but actually their vicinities are not. This is because that when black holes consume the surrounding material, the surrounding material can emit photons, and we call this process, the process that black holes consume surrounding material as the accretion. We say that black holes accrete surrounding gas or dust or other materials, and during the accretion, when the material falls toward the black hole, it will release its gravitational energy, and this starting part of its gravitational energy is transformed to like thermal energy or other energetic processes, and these processes can produce photons. So that means rapidly accreting black holes are very bright in electromagnetic radiation. But again, these photons are not directly from the black hole themselves; they are from their surrounding materials. And we have a very specific name for such type of object. We call it the active galactic nuclei. This will be the main focus of this talk hereafter. So I kindly ask you to please remember this term. It's called active galactic nuclei or AGNs. Basically, these things are referring to the rapidly accreting massive black holes, and we have obviously an illustration here showing that how surrounding material accrete down toward the black hole and emit photons. So active here means the black hole is accreting. So this is what active means. And for the galactic nuclei, it means that we found them in the center of galaxies. So these are massive, actively accreting massive black holes in the center of galaxies. Actually, you may wonder, okay, how many such things we can find, and how many massive black holes we can find in galaxies, and how do we actually find this type of object? Okay, so actually people have found the so-called active galactic nuclei in early 1960s. At that time, people still don't know their connection with black hole. They just found that there is some object like this one. It's the 3C273. It's a star-like object with large redshift. So star-like means its morphology just like star. Like here you see the Hubble image of the galaxy. It's like a point source, it's unresolved, and it's very bright. But meanwhile, it's beside a very large redshift. And for redshift, it's just an indicator of the distance of the object between the object and us. And the large redshift means it's far away from us. And we know that it takes time for light to travel across the space. So large distance also means we are looking back in time. So large redshift means larger distance means back in time. So they are identical. These are identical concepts. Okay. So this object beside a large redshift is far away from us. So it cannot be a star, and stars cannot be so bright that we can detect them at such a high distance. So it must be something we don't know at all at that time. And later on, people have studied this in very great detail and found invented the name called active galactic nuclei and said that they are actually creating massive black holes at the center of galaxies. And since then, people have established that actually almost every massive galaxy can host a central massive black hole. So that means black holes are not just some kind of exotic objects that are fun to study, but they are really important for galaxies. They reside in almost every massive galaxies. And although if we go to the low mass galaxies, the fraction will go. We found that not every low mass galaxy can host a black hole. In the plot here, I'm showing the fraction of galaxies hosting central massive black holes versus is total masses of stars, the stellar masses. And for reference, the Milky Way resides roughly here, and the Large Magellanic Cloud, that's a dwarf galaxy, resides here. And so this, so this part is very low mass. And we found that as the galaxy's stellar mass increases, they have an increasingly fraction of hosting central massive black holes, and eventually they reached about like 100%. And this was also posted at the University of Michigan News last December, showing that not every galaxy can have its own supermassive black hole. So this is very recent results, and showing that black hole demography is important. And actually, we found before that people already found that there are very strong pieces of evidence showing that black holes and galaxies are fundamentally correlated. First, in the left panel, it's basically saying that when the galaxy is larger or more massive, the black holes are more massive. So you may think of it's reasonable, right? Like you have one thing increases, the other thing increases. But actually, it's not. It's very counterintuitive. Because black holes are although they are very massive compared to our human beings, they are very, very small compared to a whole galaxy. Their total, the black hole mass only accounts for like 0.2% of a typical galaxy stellar mass. So compared to the whole galaxy, the black hole gravity is negligible. And also, let's make an analog. If we squeeze a galaxy to the side of the Earth, then the side of the black hole is only like a coin. And we found that our coin can affect the whole Earth. So that's why I say it's very counterintuitive. So that really means that there must be some physical correlations between the galaxy population and the hosted massive black holes. And furthermore, people have measured the evolution of galaxies and black holes. And in this plot, I'm showing the cosmic rate of like star formation. In a given cosmic volume, what's the rate of the star formation, and also what's the rate of the mass accreted to the black holes. We found that if we scale them a little bit, then actually they follow a similar evolutionary pattern. And again, the x-axis is redshift. Again, that means the time of the universe age. So they look similar in terms of cosmic evolution. Again, showing that black holes and galaxies are physically related. Okay, and here I'm showing another evidence. People have trying to do some simulations, to generate some fake universe, and people found that if they in their fake universe, if they do not have a black hole, then they will find many more massive galaxies than what's really observed in the real universe. So they say, okay, they really need massive black hole to regulate the evolution of galaxies. And here, basically, this plot shows the number density of galaxies versus the stellar mass of the galaxy. And this is the real universe. And this is the simulation without ATN, or in this case, without black hole. You can see that they are quite off in the mass band. So again, so this means black holes are important for the evolution of galaxies. And of course, we know that galaxies are the basic bridge of the whole universe. So this determines the black holes are very important for the evolution of the whole universe. So this is why we want to understand such things, and we want to understand how the massive black holes co-grow and co-evolve with the host galaxies. And in this plot, I'm basically showing some typical trajectory of a galaxy along the stellar mass and the black hole mass plane. You can see they both start at some low value and increase it. So the black hole mass and the stellar mass both increases with time. So this is the basic question that I want to understand. This is a very fundamental topic in extragalactic astronomy of in terms of how the black holes co-grow and co-evolve with the host galaxies. Okay, so that's why we want to understand the evolution of massive black holes. But how do they actually grow? We have like two main channels to do that. One is so-called accretion. As I mentioned earlier, it's basically the black holes consuming the surrounding gas and material, and that's called accretion. And also the other way is called mergers. If we have two black holes and they merge together into a single more massive one, they can have massive increase. So that's mergers. But as I will show later, in most cases the accretion channel that is more important compared to the merger. So I will primarily focus on how to quantify the accretion electrons. And then I will very briefly talk about how the mergers contribute to the black hole growth. Okay. So accretion. And now go back to observations. Of course we need data to quantify to categorize such things. And since we are talking about the galaxy and the black hole, because again, I said black holes and the galaxies are fundamentally related, so we need to categorize black holes together with the host galaxies. And we know a galaxy is a very complex ecosystem. It contains lots of components, and these components can emit photons at different wavelengths. So we really need the multiple wavelengths data to sample to get the holistic understanding of the whole galaxy. If we are, for example, if we are looking at the ultraviolet, we are maybe seeing the young stars. If we are looking at the for example, far infrared, we are looking at the cold stars. So something like that. So it's quite insufficient to just focus on one band. So this basically shows the single and Andromeda galaxy. You can see that the different wavelengths, different features. And among these, I would like to highlight the importance of X-rays. So X-rays, so to understand black holes, X-rays are very, very important because they are very effective tracers of the accretion power compared to other wavelengths. So there are three fundamental reasons for that. So first is that X-rays has very high penetrating power. We know that so X-rays are actually not very far away from us. I mean, in like dental examinations, dentists may use X-rays to scan the teeth. So that's just like dentists use X-rays to see our teeth. We use X-rays to see black holes in the universe. So X-rays they are actually high energy electromagnetic radiation. The typical energy is like about 100 to like 10,000 times more energetic than optical photons. Okay, so the energies are very high, meaning that they can easily penetrate through materials, like for example our hand, and this is the first X-ray image taken in 1895, where a physicist called Röntgen imaged his wife's hand with X-rays. So because of X-rays can penetrate through materials, we can use that to see our hand. But that also means that we can use that to see the black holes embedded in huge amount of obscure materials. And also, I will mention that the discovery of X-rays was made by Röntgen in 1985, and he won the first Nobel Prize in Physics due to the discovery of X-rays. And actually, At that time, the name of X-ray really just means that at that time, Röntgen didn't know what he found. He just found some mystery thing, so he just put the letter X there. And also, X-ray can also be called Röntgen wave because of this. So that's the one reason for X-rays as phases of accretion. And secondly, accreting massive black holes really emit lots of X-rays. Okay. So when almost every accreting massive black hole emit X-rays, and that structure is actually quite non-negligible. Among its total luminosities, about like 1% to 10% of them are emitted in the X-ray band. In this plot, I'm showing the ratio between the total luminosity of an accreting massive black hole over its X-ray luminosity. And it correlates with some other things, but it doesn't matter. But roughly speaking, the ratio is about like 10 to 100. So it's not huge. And so just the reference for our sun, the X-ray luminosity of our sun only accounts like 1/1,000,000 of its total luminosity. So it's almost negligible. But black holes are not. Black holes are active X-ray emitters. So that's the second reason you want to use X-ray. And the third reason, X-rays have very, very low starlight contamination. That's because stars almost do not emit X-rays. Here I'm showing the same galaxy, NGC 3783, in the optical band, in the X-ray band. This image may look more familiar to you. We have like beautiful spiral arms, beautiful bars, something like that. So that means we can see the stars, but this actually causes a problem if you want to study black holes. We can hardly separate the emission between the black holes and the starlight in the optical band. But in the X-rays, it's quite straightforward. It's just a point source. It's boring but useful. We can directly see a central massive black hole at the center, at the point source, and nothing else. So this explains why X-rays can give a clean tracer of the black hole, which I call. And also, it's also in early 1960s. Recall that it's back in like 1963, people found the first evidence of the so-called active nuclei or the star-like object. And in 1962, people found the first extrasolar X-ray source. This star is led by Giacconi, and he used an X-ray detector to scan a band on the sky, and he found, wow, there really is something here, and this is the X-ray counts versus the angle, and something really stand out. Okay, so and it's beyond our solar system. It's from something at that time people don't understand what it is. And this is 1962, and in 1967, there is a better version of that. We can see there is really a prominent peak, and it's called Scorpius X1, but it's basically a black hole. People found that, but it's not a massive black hole; it's a stellar mass black hole. But since then, people realized that the X-ray universe is not boring, because before that, people know the X-ray luminosity of the sun because the sun is close enough. And people can put some scaling. So if we put the sun to some distance, we can never detect that because the X-ray emission of sun is very, very thin. So at that time, people thought that X-rays maybe very boring, but actually no, there is something new in the sky emitting X-rays. So after that, people have been developing new detectors, telescopes in the X-ray, and eventually in 2017 we have the deepest X-ray view of the whole sky. Not the whole sky. This is only a small part of the sky. This is a real X-ray image. Again, it does not look like an optical image because X-ray image is boring, it's just point source. It's not like this. It's just something like this. But we have lots of these little dots there, and there are some, and many of them are black holes. Okay, so this image was taken by the Chandra X-ray telescope. It takes almost 20 years to do that. It's a large program, and the first generation leader was actually Giacomo behind this plot. And then people have advanced the project until like 2017 to release this product. And because of this discovery, because of the huge concentration, huge contribution by Giacomo to X-ray astronomy, he won the Nobel Prize in Physics in 2002. So this is very exciting, and I will say also this figure also actually is the very initial figure that actually brought me into X-ray astronomy. I at that time in 2017 I was a sophomore student, and this results just came out, so it's very exciting for me. So because of this I entered the X-ray astronomy, and now so you can see that between 1962 to 2017 it's only like 60 years, 6 decades. And it's really amazing to see like how many improvements people have made from a plot like this to a plot like this. Okay, that's amazing. And the sensitivity from this plot to this plot increased by a factor of 1 billion. So, and right now, the X-ray astronomy is still a very important field in astronomy, in the whole astronomy field. And this is the latest data. People have counted like how many citations people have made. The telescope have contributed, and this is for the latest papers published in 2025, less than a year ago. And among 20 of the most cited telescopes, 5 of them are X-rays. So X-rays are still very important for us to understand black holes. So so I've talked about why X-rays can be used for black holes, but how do we actually do the observation? We need some design. We cannot just randomly point the telescope to a random position at a random time. We need some design, and the design of doing observation is called cosmic surveys. People have been following the so-called wedding cake design, and that basically means that people observe areas of sky with some patches divided into different layers. So we have some deep surveys, and the common area is smaller than the full moon size, so it's very, very small. But people spend lots of exposure within those small regions, and so it gives the higher sensitivity. And we have shallower layers like the median layer, and median layer is roughly like more than 10 times of the full moon size. Its angle increases, but the sensitivity decreases. And we can have such a layers like this if we people increase the area and decrease the sensitivity of vice versa. So that's called wedding cake design. And the reason for that is that different layer can give you different information. For example, if you want to go deep, then we certainly need a deep layer. But if we want to find some real object, then we need a huge sky area. So we need the wide layer. So that's the idea for that. And here I'm showing the existing X-ray survey on the x-axis. X-axis is the survey area, and y-axis is the sensitivity of the survey. And you can see at the top right we have survey cover larger region but shallower sensitivity. And if we go to bottom left, we have deep survey covering small area. So this figure, the deepest X-ray view of the sky, it corresponds to this one, the CFS. That's a very deep survey. And now with these surveys, we can now begin working on the black hole growth. We want to measure the cosmic growth rate of the massive black holes. And here I want to mention that for black hole growth rate, I'm referring to the long-term one. So the basic idea that, as I said, when a black hole accretes surrounding material, they can also emit photons. And the rate of it emitting photons is proportional to the rate it consumes surrounding gas. So that means that if we measure the luminosity of accreting massive black hole, then we can use that to infer the mass growth rate of the black hole. But this mass growth rate is instantaneous. In the across the whole cosmological timescale, this instantaneous growth rate can fluctuate a lot. Here I'm showing the growth rate versus the look back time. Because it really fluctuates for several orders of magnitude. And for cosmological context, we need the long-term ones. We need to smooth the curve like this. We need to get get rid of all these spikes. So how do we do that? Basically, just average over the galaxy. So if let's say if we have within a survey field, we can detect let's say 1,000,000 galaxies, and then we may only find a few thousand of the active galactic nuclei emitting X-rays. So most of the massive black holes in galaxies cannot be directly detected because they are dormant. They are not active accreting. But we think that there is no fundamental difference between those are fastly accreting and those are not. We just happen to capture the phase that some of them are accreting, some are not. So we want to average this out. So we average over the sample, we average the detected black hole accretion power of the whole galaxy population. Then we can get the long-term black hole growth rate. So this whole problem is really a multivariate problem. So here we need the aging accretion power, and we also need the galaxy population. So we need X-rays to give us the accretion power of black holes, and we need multivariate data to give us information of the galaxies. So we need to combine them together. So the actual underlying data is very intensive. And in our recent work, we have compiled data after like 2 decades of accumulation in several best categorized survey fields. We have 1.3 million galaxies selected. Among them, we detect 8,000 massive galaxies, massive black holes in the X-rays, and use by averaging the accretion power, we can derive the long-term black hole mass growth rate as a function of the galaxy stellar mass, and also redshift, and again redshift means the cosmic age. And we can see that as the mass galaxy stellar mass increases, black holes are also accreting faster, and we see that at a different cosmic age, the black hole accretion rate are also different. That means at younger ages, massive black holes are accreting faster. And so this is gives a very quantitative assessment of the link between the black hole growth and the galaxies. And based on that, we have done some follow-up analysis. For example, we explain why, as the universe ages, why the black holes are hitting the rate of growth. And this was also posted as the Universal Michigan News just last month. And again, so as I mentioned, so black holes correlate with galaxies fundamentally. But here I'm just showing a very simple correlation. That's the black hole growth correlates with the galaxy stellar mass. But there are also many other parameters like the rate of the stars that formed in the galaxy, and the galaxy morphology, and the environment of the galaxy, the stellar age of the galaxy, etc. So there are lots of projects that I cover, and they have been actively investigated for recent decades. So it's a very exciting field, and we are certainly pushing forward to understand the how black holes and galaxies are correlated. And so that part is about the accretion. And as I mentioned, there is another way for black holes to grow. They can grow through mergers. So in this, I'm going to only very briefly talk about mergers. So black hole mergers can hardly be detected. We can't detect them through gravitational waves, but its constraint now is still quite loose. So we just infer the merger information from cosmological simulations. Okay, and we can derive the merger-driven growth rate. And in this plot, I'm showing the growth rate versus the galaxy stellar mass, and different panel means different redshift or different universe age from this to this direction. We are looking at the older and older universe. So this is the universe now. This is about like 10 billion years ago. But the red curve is the accretion-driven growth of black holes. It's basically the same thing here. It's just these curves here, but just plotted in a different panel. And the blue curve is the merger-driven growth rate for black holes. And you can see that in most cases, the accretion-driven growth is higher than the merger-driven growth. I mean, because the red curve is above the blue curve, and only in some limited parameter space, like here, we have the merger-driven growth to be comparable with the accretion-driven growth. So at least this tells us this is what I mean by earlier by saying that the accretion is the more important growth channel for black holes. But now we have two growth panels. We can get the growth rate. Then we can quantitatively answer an important question: how do supermassive black holes grow get supermassive? We can reconstruct their whole evolution. And this is an important result. This was presented in like 2 years ago in the Astronomy American Astronomy Society press conference, and I'm here. Basically, the idea is that we combine the observed accretion channel and the simulated merger channel to get a holistic understanding and the realistic reconstruction of the black hole growth across cosmic time. And for example, here I'm showing the black hole mass versus, again, this basically cosmic age. You can see that how it grows from earlier universe to now. So this we can quantitatively reconstruct this trajectory. And in this part, I'm showing the whole population of massive black holes. This is the mass density of black holes. That basically means that within a given cosmic volume, what's the total mass of black holes within the volume? And I plot that as the function of the black hole mass. And you can see that there's a different cosmic age. It increases from younger universe to the older universe, and kind of froze at about z1. That's about 7 to 8 billion years ago, and it's just remained frozen because the black hole growth rate is pretty low in nowadays. Okay, so this is how we really eventually quantify the black hole growth and their population. And in the last part, I want to talk about the future. How can we push this forward? And I will talk about this in the context of the Rubin Observatory legacy survey of space and time. So this is a very, very important observatory for the whole astronomy society. It's basically a foundation project for the next decade of astronomy. is the top ranked large ground-based project in ASCO 2010 decadal survey. ASCO 2010 decadal survey just means that in around like 2010, astronomers think how do we push the discovery machine forward. Then Ruby is one of the top ranked one in on the ground. And Ruby Observatory is an optical telescope. It will observe the whole southern sky marked here. But the key idea is that it will observe that repeatedly. So it's a time domain machine. It will not only just take pictures of the sky, it aims to take videos of the sky. It aims to discover like how the sky changes and how the objects on the sky changes with time. This can give us a new discovery regime for astronomers. And actually, just last year, this is Ruby Observatory has already released the first image. This is the real Ruby data, and it's again in optical, so it's looks more beautiful than X-ray images. And for us, the Ruby Observatory is important because it really helps define the survey data. Okay, it has motivated the production of lots of cosmic survey data, and by that I mean like 10 or 20 years ago, people have decided, oh, Ruby is going to target some specific area, then people can begin accumulating data in those areas in preparation of Ruby, and this makes some of the Ruby fields to be the most important survey fields. So this is actually the underlying data I've been using for my previous results. But again, this just follows the Wedge-cake design. You have this deep layer and the median layer, etc. And you can see that in the median layer, we have the Ruby LSST. DDF means deep drilling fields. These are all defined by Ruby. So these are very important fields because thanks to Ruby. And you may have heard of the James Webb Space Telescope. And I would say it's actually complementary with Ruby. So JWST is certainly the most expensive telescope we have ever built. It's very compelling, but it only probes the deep layer of the Wedge-cake design. Okay, so to complement that, we need some other telescope like Ruby. So Ruby works in the medium and wide layer. So JWST is not competing with Ruby, so that instead complementary with each other. And here I'm going to show some basic facts of Ruby, how it's designed, what's some technical parameters. So it's located in Chile, in the southern part of the Earth, so that it can survey the southern sky. And its primary mirror is about 8 meters. And the mirror weight is about like 10 cars. It has a very powerful camera, about 2 cars in terms of weight. And the camera contains like 3.2 billion pixels. That's a huge number. And the Ruby will also have a very large field of view, like 10 square degrees. That's about like 50 times the formal. So, and also it takes about like 30 scans for Ruby to do a single exposure. And when the Ruby point moves from one point to another point, it takes roughly less than 5 seconds. So this is really amazing because this thing is of course very heavy, and you have to make sure that this fast move will not cause distortion or something like that. So this is a remarkable engineer problem, and I'm grateful that engineers have worked this out to make this a real powerful time domain machine. Because of this, Ruby can observe the dynamic sky because it observes the sky very fast. And also the Rubin Observatory, the actual survey is called LSST. It's called Laboratory Survey of Space and Time. It takes about like 10 years for Rubin to do the survey. The sky area roughly half of the sky, and a typical pointing will be covered by Rubin with like 800 times. So that means every 3 days, Rubin will observe the whole southern sky. So that's very fast. So that's what I mean, that Rubin will not only give you a picture of the sky, it will actually give you a video of the sky. And meanwhile, it's producing lots of data, because you can see that we have 3.2 billion pixels for the camera. And so the data size is very, very large. In a single night, you can produce like 10 terabytes of data. And for reference, my computer here is a total capacity is like only 1 terabyte. So I need 10 computers to cover a single night of moving data. So eventually, after 10 years, it will produce like 15 PB in total. So this also causes lots of problems for data scientists, for like how do we actually store the data, how do we analyze such an amount of data, and that's also a good chance for AIs to get into that, to do some mining, data mining. So there are lots of challenges, but it's very exciting. And eventually, after 10 years, Rubin will observe 20 billion galaxies, 17 billion stars, and 6 million small bodies in our own solar system. And regarding the alert, so alert just means that when the Rubin finds something changing on the sky, then it will produce an alert. So an alert just means that something changing on the sky. So every night it will find that there are 7 million points on the sky change with time. And eventually, over 10 years, that's 20 billion. So it's really a dynamic sky that will be discovered by Rubin. It will be a totally unexplored private space. So it's very, very exciting. And here I'm giving a very, very brief history of Rubin. And for lots of these, I don't know the details at all. But people have been thinking about Rubin like 30 years ago. And for scientists, the most important milestone is 2009, where the first science book of Rubin was released. And in 2018, scientists began to think like how to actually design the survey, how to tell Rubin to, like for example, how should they map the sky. And we are now at like 2026, and Rubin the Rubin data is arriving momentarily. So last year in 2025, last summer, we have the Rubin First Light event. That's a global event celebrating that Rubin finally produced the first image. And this is the first image. And we have a nice cake celebrating the Rubin first event. We have the same thing in Ann Arbor last summer as well. And in the same month, Rubin Data Preview 1 was released. It's not based on actual Rubin camera, not actual LSST camera. It's based on small camera called commissioning camera. Main aim to help engineers to understand the whole system, to make sure that everything is going on well. But it's great to see that there's some official data released last year, and in February this year, Rubin produced the first scientific alert, and that means Rubin finally for the first time identified that something changing on the sky, and this alert, the alert is very complex because you need lots of whole system to generate alert and analyze alert and announce that. So it's a very complicated thing. There are lots of groups specifically working on the alert. For example, Google is involved in producing the alert, and I think there are 4 independent groups producing the alert in total. And and right now it's April, and within less than half a year, Rubin data preview walk 2 will be released. And this is the real Rubin and real LSST camera. LSST camera means this huge camera, 3.2 billion pixel camera. So this will be useful for scientists. This will be as so again, data 1 is for engineers, data 2 is for scientists. So we will begin to work on the science with Rubin starting just half a year from now. And after 2 more years, Rubin data release 1 will be released. That's the first year of the Rubin observatory data, and more and more will come in next 10 years. Okay. So that's very exciting. And among them, I would say that one very important component is the debris field of the Rubin. So again, I said Rubin will serve the whole southern sky, and that's very wide. But it also picks about like 5 debris fields. It will observe these small patches of the sky with higher cadence and with much deeper depth than the wide survey. And these debris fields will be very useful for constraining the black hole growth, because it's deeper. That means you can go back earlier in time. And these debris fields have, again, I mentioned earlier, has actually served the foundation for the science given in this talk. And this is plot in one of the debris field in 2018. This is the planned. At that time, some of the surveys were planned, and many of them have already been finished. You can see that people are really putting lots of resources in the Rubin debris fields for the science. And eventually, Rubin itself will spend like 7% of its time within only like 5 debris fields. Okay. So that's so lots of data are already public, and also more and more is scheduled for these debris fields. For example, of course, this includes Rubin. We have other important surveys like Euclid, SPSS, etc. And I want to mention that in our own department, University of Michigan, we have a specific small spectroscopy survey covering one of the Rubin debris fields. So basically, Rubin will give us lots of exciting news, I believe, in the coming months, hopefully. And that's basically the talk, the science part of my talk. And at last, I want to say that I only covered a very small part of the so-called active galactic nuclei and the massive, the accreting massive black holes. And on YouTube, there is a very, very nice video series released recently, only 2024. I give a very comprehensive overview of active galactic nuclei. You can just search that. It's coded by Professor Neil Brandt. And I will stop here. Happy to take any question.
Thank you so much, Doctor. That was a really, really interesting presentation. I appreciate it. I do have one, it's a simple, straightforward question. You mentioned that the black holes seem to attract light, and they're so massive and there's so much gravity that they really don't allow light to escape.
Yeah.
Okay. However, in the 1900s, Eddington viewed an eclipse of the sun, and he observed that a star behind the sun was able to be seen because the light from the star went around the sun and then came to us. And if gravity attracts light, how come that star, the light from that star was repelled from the sun instead of being sucked right into it, and he would have never seen it?
I think that's a great question. So So actually, when I was saying that light cannot escape from the black hole, that means they cannot escape from inside the black hole. I mean, once the light is fall into the black hole, then it cannot escape. But if it's out of the black hole, then it can.
But surely there should be some light behind the black hole.
Yeah, so it's like actually this part.
And wouldn't that go around the black hole, not into it, just like the light from the stars went around the sun instead of going into the sun? So we should, by right, if Etienne was correct, be able to see light coming around the black hole, which we do in a way. We see the accretion disk, but that's should only be part of the light, right?
Yeah.
The gravity wouldn't have any effect on light except to repel it and drive it around the black hole. So we shouldn't be saying that gravity is so strong that it won't allow light to escape, okay? The light was never in there to start with. Is that correct?
Yeah, so I think when it's correct, so this is, I think you mentioned the accretion, we can see accretion disk, like it's basically this spot we can see accretion disk, this produced by the curvature of the light trajectory, the photon trajectory because of the gravity. So that's the same thing that happened to the sun, except that the black holes are more massive.
Okay.
Yeah. So
you are not saying that the gravity is so great that it draws in light. You are saying is you should be saying what Edison said, that light is driven around the black hole, and if there's no light coming from the black hole, it means it's never there to start.
Yeah.
Okay. I think I've held up enough for this meeting.
Okay.
That question. Thank you so much.
Yeah, I think what it is, once you cross the event horizon, then light can't escape. But the accretion disk is outside of that.
Okay. No, we see the light from the accretion disk. We should
Right.
be able to see under
But
that.
not inside the event horizon.
It would just be added to it. It would be a minor part of it, but it would still be there. But I do have another kind of question to you. We've heard of neutron stars, where it seems the gravity is so enormous that it drives electrons right into protons and forces them to become neutrons, which makes the neutron star. Is there any talk in black holes about the pressure being even so much greater than in a neutron star, okay, that the actual electrons and the neutrons are driven, and by the way, I also include not only the electrons, but the positrons are driven into the black hole to become positroniums. And the black hole is really a positronium star.
Yeah, that's a great question. So yeah, you have good understanding of the neutron star, and for black holes, the matter of the black hole is already not in. It's not already regular matter. It will not be neutron, electron, etc. It's basically in the general relativity, it's basically an infinitely high density at the center, at the single point, and there is no normal matters in that can be made out of our things.
Okay, so there's no real talk about what the inside composition of a black hole. Okay, thank you.
Yeah.
On slide 21, you mentioned it after, but about the 8 billion year mark, there's that sudden drop off, like between 7 and 8. There's like a relatively aggressive like drop off, and you mentioned it was like due to the accretion disk and kind of the limiting factor on the size of the galaxies. But why was it at 8? Why didn't it happen right at the beginning, like when everything was in hyper expansion?
Yeah. So for this, I think it's kind of I just pick a random galaxies kind of it's not physical. It's just happens to be there. So yeah, you can. Yeah, but
So it's nothing like the size of the universe affected it, or the amount of matter.
Yeah,
that's
no.
not eaten by black holes.
yeah, it's
Okay.
not.
So it's not because of the black holes that
Yeah.
drives off.
Yeah. But I do want to mention that something kind of happened here is roughly around the so-called cosmic moon, and after 8 billion years ago, the overall accretion rate of black holes are decreasing. That's a population level protein. Yeah.
Is it possible for gravity to exist without being emitted by a massive body?
Can I say that again?
Is it possible for gravity to exist without being emitted by a massive body?
Mass. What's the last words?
Body.
Massive
Body.
Oh, okay. Yeah. I mean, as long as something contains mass, it has gravity, so it's everywhere.
But can the reverse be true? Gravity exists without the mass?
I don't think so. Yeah. But I mean the mass and the gravity basically, according to general relativity, is basically the same thing. It's basically the curvature of the space-time. They are not two distinct things. They are fundamentally the same.
Thank you.
Yeah, thank you.
Any other question?
No, and when black holes are accreting, is there some limit as to how far they reach to do the accretion? Will they run out of material at some point? Is that why there's a certain phase where they're active versus later on they're not because they can't pull in enough material to excite and glow?
Yeah, exactly. That's the key problem. Yeah. Black holes stop accreting because they run out of gas, and actually that's it's actually a huge problem in astronomy. Why black holes can't accrete? Because at the galactic scale, the material resides in a very large distance. Then black hole is very small, so you have to drive material from very far away from black hole down to the center.
And there's a lot of angular momentum to
Yeah.
spin off too as the radius decreases.
Yeah. So that's a big problem. Yeah.
So still more questions, right? More things to research.
Yeah.
So he gets to keep his job. Do we have any audience questions, Zoom audience? Can anybody in the Zoom audience hear us?
Yes, they said the sound's good.
Okay, cool, good. Doc,
I guess it makes me think of a question. What comes first, the black hole or the galaxy? So does galaxies form, then black holes are created? Or was there black holes and then the galaxy forms around them? Do we know what comes first?
That's a very good question. That's the most fundamental thing in astronomy, and people do not know that right now. But let's basically ask how the first galaxy and how the black holes are built, and for black holes, we have some theories for the initial black hole seeds. Basically, there are three theories, roughly. One is they are produced by very massive stars. In the very early universe, stars can be very massive because their metallicity is almost zero. And metallicity is zero means that stars cannot cool. So they can grow huge, very large. And this can produce very massive remnants of black holes. That's one way of producing initial black holes. And the second way is that we have star clusters. They have lots of stars, and they maybe produce a single black hole from that star, and this. And there are lots of small black holes created because of their stars, and then they collision together and form a single black hole seed. That's the second way. And the third way of doing that is also there is no analog for the third way. In the local universe is that we have a huge giant cloud directly collapsing into a black hole because it has no metallicity. It's very hard to cool. It's very hard to segment, so it can probably directly collapse to a single black hole. And yeah, that's the current theory, and we don't know which one.
Thank you.
One question I've always wondered: do black holes ever stop being black holes? Like if they consume so much matter, do black holes ever like cease being black holes? Like if they consume like so much matter that they can't take any more in?
Yeah. I don't think there is a theoretical upper limit for the black hole masses, but it can like regulate itself because, for example, if it consumes too much gas, then there will be nothing for it to grow. And also, when the black hole grows, it can emit lots of energy that can drive lots of gas away from the black hole. Yeah. So this kind of self-regulated itself. Yeah.
So no physical limit, but a physical process may limit how it grows.
Yeah.
The other side, black holes evaporate by Hawking radiation.
Yeah.
So eventually, a time scale of maybe 10 to the 100 to 10 to the 1,000th years, the black holes evaporate.
Yeah, that's
That's
that's one way of doing that, and it's argued that we have the so-called primordial black hole that produce in the early universe, and in theory can produce emissions through Hawking radiation, and people are still looking for the signal.
I think Fred Adams would have an opinion on that, right?
Yeah.
For his cosmological evolution, right?
Yes.
Dr. Adams, right?
Yeah.
So if black holes absorb gases, do they ever explode?
When once the gas enters the event horizon of the black hole, it cannot escape. But before it enters the black hole, there are lots of energetic processes that can drive material away from the black hole.
Oh, okay.
Any other questions? Don't see anybody from Zoom. Thank you very much, Dr. Shaw. With our appreciation, we'd like to present you with a Lowbrow.
Oh,
Sure.
You're
You're very welcome.
Yeah, I appreciate it.
You're very welcome. At least we can do. Okay. So, our first order of business is we have a couple of things to vote on. One is officers. I did a little survey of the current officers, and everybody that is an officer did say that they were willing to go on for at least another year anyway. So they're all candidates. But with that, before we take a vote, there's anybody else that would like to run for any of the offices?
All room for more.
Yeah. And as usual, everybody freezes. If you twitch, you're elected.
If you're not, you're elected.
So with that, everybody that's in favor of the slate as presented, please say aye or show of hands. Is anybody opposed? Okay, Well, we didn't get out of it, did you? Oh, well. Thank you very much. The next item is, you remember a couple months ago, I sent out an email about increasing, it was a bylaws amendment to increase the amount of money the officers, now the officers have to approve it amongst themselves, but to increase that from the $250 limit before we'd have to ask for the entire membership vote to $500. I also discovered something in the bylaws that had escaped me for a while. We did write those a long time ago, that we could vote via email. And I'm kind of sorry that I found that, because once I hit it, you can only imagine my inbox exploded. But anyway, there were, I believe it was 38 email votes, and all of them voted yes. So we effectively add those to what we take tonight, which I think is pretty obvious what's going to happen. But with that, anybody that's in favor of raising that limit, please say aye. Anyone, okay? Is anybody opposed? Okay, so it shall be. Thank you very much. And I believe that's all I had. So I will pick on Jeff.
So both motions.
They passed, yes, you passed. Yeah.
We didn't do things like. A motion. I guess because we published it before, we have to do that for this time, right?
Yeah, because that effectively was, yeah. Motion. So.
As published previously.
Yeah. Yeah, that's a good way to word it. Thank you.
I'm gonna probably defer a lot of the left stuff to Tim and Barry, since they've been working hard, and congratulations to them for getting the new site online and getting this off of the HostGator. We're still in literally the next 5 days. We'll figure out how the young astronomers domain is getting migrate magically over. There's been administrative back and forth on a lot of things, but it is currently supposedly cooking away tonight. You'll know by Tuesday night probably on that. I get that right, Barry?
Yep.
And Jack?
Yep.
I don't know, I was on a ship for a lot of March and whatnot, so I don't have a whole lot extra to report, but I do have 3 manuals, RAS manuals, and 6 calendars that are left. 26 and 21, if I remember correctly. So if you're interested, come see me, we'll figure out finances.
$46 and $21.
Yes.
Not quantity.
Yeah, quantity is all of what you see here.
Then no.
Yes, it is. I can carry the backpack without hurting myself. I don't have anything. We're going to be in Algonac, can't say it right, in I guess a week from now and all that. I'm looking forward to looking across at nothing for some black skies. There will be telescopes taken.
And picking on the front row. Yeah, was that Jeff?
Yeah.
Okay, thanks.
Yeah.
The only report that I have is I recently finished the book Gemini, which is by Jeffrey Kluger, who wrote Apollo 13. And I can highly recommend it. And it talks both at some pieces from the Mercury program and some pieces from the Apollo program that explain how Mercury fits in between the two. It was Gemini that actually taught us how to work in space. And it was actually far riskier than they had thought it was going to be. There were a lot of complications. Fortunately, there was 2 astronauts that lost their life in a jet crash, 2 Gemini astronauts, but no one was injured very much in any of the space activities. So anyway, good book, highly recommended. And that's really all I've got. I will be a greeter for the open house tomorrow. So I'm out for one.
Check.
You said.
Yep.
Little leader. And will this show over the
No,
Not over Zoom.
We'll find out.
so
Yeah.
Well, we haven't figured out how to do that yet, but
there's probably a way to make it go, but you gotta get it programmed the right direction.
let's get this to go this way then.
It's on both.
Yeah, on the screens here, you can see.
Oh, I see over there.
Yeah.
You can actually do sourcing.
Are you gonna try?
Okay. First of all, we're gonna talk just a couple minutes about the deck walk that we built out there. Some of you may remember this. This is in the club's newsletter here. They talked about it, me, Don Foy, and Joe Forrester were out there measuring some things, and some ideas how we wanted to build a deck walk out there. Okay. What we did do is during the rain and everything, I just put everything in my garage, bought all the parts and everything, did a pre-assembly, cut it to certain edges. This end here has a 10-degree cut on it, and it has to do with how it sits on the concrete stairway coming out of the observatory. After that, wait until we had a clear day last week in between the rain. I ran out to the observatory and we started digging the trenches, putting the 4x4s in. These are rods, re-rods. Got this all leveled out, pounded down with re-rods and everything. We did some more work with it. And finally, after that, it all taken care of. Did manage to put in, these are 2x6x4 foot. This is not the 1-inch plank wood that goes on your deck wood. Standard 2x6, which is a lot more stronger. It's going to make it a lot more, it'll just last longer. It's going to make it a lot more stronger. The other argument is, when we had this design, we talked about getting a wheelchair up there and taking the 17.5-inch telescope out and everything like that. All right. We did come out and do an angle measurement on everything. It's approximately 10 degrees. We're looking at 9.8 or something based on the wheel chair value. And anyway, so it comes out to 10. So we should be good getting wheelchairs up there. If somebody wanted to come up for a wheelchair, we should be able to take them up there without a problem. That's everything we did. And
So one comment, I believe the plan is to take all of this, these pictures and things that you had sent to the officers and incorporate it into the upcoming newsletter. I think that was what Amy was talking about.
yeah, I do have an article I wrote for the officers. But we're gonna take that and revise that and it'll be in the newsletter and everything.
So even if you didn't catch all the details, you'll be able to read it in the newsletter.
It's just that the only other thing, this is how far the flooring sticks out or the deck walk sticks out. Like if you're walking down to the edge of the building, you can still drive over it. And we're gonna put up some kind of
Reflective tape.
yeah, like a reflective base of some sort there. So if you're driving, you'll see it, or if you're walking, you'll see it. Just that's where the deck starts and you can walk up it. But other than that, that's all I have to report on that.
Jack is multi-talented, isn't he?
It's got the bruising to prove it too.
Yeah.
Not good there. Quick one. We did go out last Sunday and take out the secondary mirror off the McMath and cleaned it off because it's been out there for 12 years.
Yeah.
So we did just, some people have always asked what it really looks like. Let me make this less zoom.
Looks like it needs recoding.
No, this is the back, not the front. This is the back. That's how you screwed it on the cylinder. And that's what it looks like when you take it off. And I'll explain the other reason why we went through all this. Yes. We did work on cleaning it and everything. And some of you know, these are data wipes, data from Data Optical. They use this for cleaning off lenses and mirrors and everything. We cleaned it off, got a little more shiny. But then here comes the interesting part. As some of you know, I did spend some time going back to the Bentley, getting the original design of the secondary mirror because I wanted to figure out the optical focal length and everything of it. the true design. So Tom Ryan has a special device here that will measure the radius of curvature of the secondary mirror. So he brought that out there, and we actually went through and measured it. We got some hard numbers, but very similar to the numbers that McMath wrote in his document when he wrote this back in my dad goes back to 38, 39, so they were designing it. So it comes out within, I would say, about the radius of curvature on the secondary mirror from what we gained from this measurement, what McMath had. It's about less than 2 inches of radius, the difference in the radius and curvature. So it's very, very close. So that worked out quite well.
Was the secondary, pardon, was the secondary replaced?
No, that is the original secondary. I wanted to get the actual design and understand the radius of curvature of that secondary mirror.
You know, now that I think about it, we've never recoded the secondary, have we?
It's been recoded the last time.
Did you send that to?
Yeah,
Oh, okay.
out to Flathead.
Yes.
And it still looks good when you clean it off, man. Some minor surface scratches. I don't know where they came from.
Hmm.
This is the only thing that might be, if some of you may get in the mail. This is from our good friend on the lawsuit between Celestron and Meade when they were trying to control the price of telescopes and that. So there's a litigation. They sent me a notice. I did not buy a Meade or telescope in that time frame, but I have bought some parts from Celestron. And this was a litigation. So some of you may get this in the mail. And it has to do with the
Price fixing lawsuit.
yeah, price fixing is really what they were doing, and they won the case. So there's a litigation against them going on. You may get this in the mail. I got one. I imagine some other people would. Other than that, that's all I have to talk about. And that's enough.
A lot of work, Jack. Thank you.
We'll work everything out.
Yeah,
I had no.
that was quick.
No.
So hiding behind Don, we have Barry. Anything, Barry?
Nope, I'm good.
Okay, Tim?
I guess we, Jeff said, the public part of the website is up. We did add a webmaster contact form.
Yes.
So if there's some content things that you want changed, added, whatever, fill out that, and that goes directly to the two of us. There's the contact forms, I separated them so they are embedded within the outreach pages, so wherever someone may land wanting outreach, that form is the same, so that will go to the Ask the Lowbrows at Gmail. I don't know who monitors that, it's not me, so I think based upon we had the request from Ipsy District Library, I think came from that. So that part's working. I've received a web request. We do have one little bug that the two of us are working on. It seems like the event calendar, like today's meeting, disappeared from the event calendar this morning. It was there yesterday. I looked at it. And this morning it disappeared. So it's a date thing. We're working that out. For a stopgap on this for tomorrow's open house, I'm gonna check in the morning if it has disappeared from the current events calendar. It just means that the website automatically just deletes stuff or takes it out of being able to see it.
That's what I'm wondering.
On the day. Yeah, and then, anyway, there's something in there that's just crazy. I'll just put a banner on the top and make a direct link so that tomorrow it is still visible about there. So the public, like I said, the public part is done. Barry's working on the building the member part. Doug's Mobile has sent us a preliminary membership list. So that data will get in. I think we're kind of right where we said we would be.
Yeah.
Excellent. construction projects are always behind you. You're saying that we're actually.
I did have there's one thing I just wanted to throw out. I don't know if it really needs any discussion. I know, when we were talking as a board about your 35 emails. Voting and things, a lot of organizations I belong to vote electronically. Would that be, and it can be something as simple even as a Google form, because those do timestamp and. You can require specific information so that you can have a record of when someone voted and who voted, or somehow, maybe it wouldn't, I don't know. Like I said, I'm just something that we might want to just kind of explore.
Take a look at it, sure. I bet Jim's got, you done, Tim?
Yeah.
Oh, okay. I bet Jim's got some.
Tomorrow night's open house, skywise, it will probably have. It will be cold, wet, and a bit windy, so I'm dressed for it, because it's gonna be rather challenging physically. But nobody's been out there since the storms. So we don't know if the road is open. Either Jack or I'll get out there in the morning and find that out, and then post whether the open house is happening.
Okay. Do we have enough?
We'll still get an email tomorrow.
There will be an email.
We have enough of us coming to.
There's enough people that have committed to being there. Jack said he will open the observatory. Ken's gonna greet, they're gonna be there, and I had one or two others that said they'd be there. And I know that there's some other folks that are planning to come up there. So I think we'll be all right, member wise. Public tends not to come out in such force when they know it's a bit wet, cold, and windy, so.
I was just taking a look at the Astrospirit and don't get discouraged by the early weather earlier in the day. It does seem to clear up, but it's gonna make full. It starts on the 10 o'clock, so.
Everybody, all these forecasters I look at, they're pretty much in agreement that we'll have stars. But we could have raindrops until 4 or 5 o'clock in the afternoons. It's definitely going to be damp. Anywhere's from 10 to 15 mile-an-hour winds. And well, much better, but temperatures after about 10, 11 o'clock in the 30s.
Does anybody have anything else? In that case, I would entertain a motion to adjourn. See, nobody wants to adjourn. Does anybody opposed?
We're gonna leave. We're all
Charles, oh my God. I fall asleep on tape.
Right.
You're sleeping there.
All right.
Thank you, everybody.